Hello, everyone. Firstly, I would like to thank the organizers of the seminars for the kind invitation, especially Aisha. My name is Nikolaos Pallikarakis. I'm a postdoctoral researcher from Greece, from the Department of Mathematics of DUA. And the title of my presentation today is Exploring Universal Eigenvalue Problems through Machine Learning. So the outline follows. After a brief introduction in the two different eigenvalue problems that we're gonna discuss today, which are the Sturm-Liouville eigenvalue problem and the transmission eigenvalue problem, we're gonna briefly discuss about well-known methods for the numerical solution of the direct problems for both of them. And then the main part of my talk is gonna be about applying machine learning regression models to solve these specific inverse eigenvalue problems. I'm going to give some ideas behind supervised machine learning for regression and also briefly discuss the three different models we implemented for this case, which are k-nearest neighbors, random forest, and neural networks. And finally, I'm going to show some numerical examples for the inverse Sturm-Liouville eigenvalue problem of symmetric potentials and the inverse transmission eigenvalue problem for piecewise constant index in disks. So, as you probably know, direct spectral problems are problems for which we're trying to find the eigenvalues and the eigenfunctions of a differential operator for some known physical properties of the medium. While then in the inverse problem, we want to recover these material properties or physical properties from known spectral data. And the most classical and well-known example is the Sturm-Liouville eigenvalue problem, which stems from the vibration of a string, which can be fixed in the edges. And by applying separation of variables in the vertical displacement, which satisfies the wave equation, it's well known that we end up with a boundary value problem, which is the Sturm-Liouville eigenvalue problem with Dirichlet conditions. And with this row of x here, we denote the non-constant density of the string. So for this specific problem, when we study the direct problem, our aim is to study the existence and the properties of the eigenpairs for a given potential, while also we're interested in numerically estimate the eigenpairs. And it's well known that this problem satisfies some very good condition because there exists a competence of adjoint operator associated with this differential equation. And as a result, a lot of numerical methods have been developed to compute the eigenpairs. In the inverse problem, one important question is the uniqueness associated with this, which is whether one can uniquely determine the unknown density or potential rho of x from a knowledge of one spectrum, one infinite sequence of eigenvalues. And additionally, we're numerically interested in reconstructing the rho of x by finite spectra. Of course, the uniqueness is studied many years ago by Borg initially, where it is known that when the rho of x is symmetric, uniqueness is verified from one spectral family. And in other cases, like non-symmetric or discontinuous refractive indices, we need two different families of spectra, for example, to uniquely recover the rho of x. And additionally, for the numerical solution of the inverse problem, there have been several methods to do it from finite known eigenvalues. For example, the well-known paper of Randell and Sachs from 1992, and many more afterwards. On the other hand, the second problem we discussed today is the transmission eigenvalue problem. This is a different problem. It is a boundary value problem for a set of equations, W and V, which both of them satisfy the Helmholtz equation. And the first one is the non-homogeneous Helmholtz equation for a function n of x, which for us is going to be the refractive index of the medium D, which D is usually assumed to be having a Lipschitz boundary and to be simply connected. And also, these differential equations come together with the boundary conditions, which are transmission type in the boundary. The complex values of k for which there exist non-trivial solutions of this boundary value problem are the so-called transmission eigenvalues. This problem is a non-standard eigenvalue problem and it's not self-adjoint, and as a result, much more difficult than the Sturm-Liouville. And this eigenvalue problem comes from the acoustic scattering problem of the inhomogeneous medium D, where it is shown, and for example, I refer to the classic book of Colton Gress, that the far field operator associated with the acoustic scattering is injective and has dense range if and only if the corresponding wave number k of the acoustic scattering is not a transmission eigenvalue for a pair of solutions W and V, where V happens to be a Herklotz wave function. So this eigenvalue problem is coming from an application of acoustic scattering. And for the transmission problem, in the direct case, we try to study the existence and properties of the eigenpairs for a non-refractive index, and also where we want to numerically estimate these eigenpairs for this refractive index. And as I said before, this is not a standard eigenvalue problem, and as a result, it was existence and discreteness of the spectrum was an open problem for many years until 2010. It was solved by Tsakoni-Kitidis and Hadar, where those authors showed that indeed exists an infinite discrete set of real eigenvalues for under some restrictions on the refractive index. And since then, several numerical methods to compute the eigenvalues have been developed. On the other hand, on the inverse spectral transmission problem, we firstly study the uniqueness of the inverse problem on whether the one spectrum can uniquely determine the refractive index, and we also want to reconstruct this refractive index by using finite eigenvalues. For the uniqueness, this is studied only mainly in the case when the refractive index is symmetric. A lot of papers have been written about this subject. I also submitted a review on this recently. And in the case when the refractive index is non-symmetric, uniqueness is open. And as a result, only a few numerical methods have been developed for the inverse, numerical inverse problem, mainly due to the lack of uniqueness result in general domains, and also due to the complexity of this eigenvalue problem. Now, we're going to briefly discuss about the numerical solution of the direct problems. As I initially said, for the Sturm-Liouville problem, there have been developed several approximation methods to solve the direct eigenvalue problem. For example, in the classic book of Peirce, some more recent methods like Neumann series of Bessel functions from Kravchenko and other researchers, and even we have even software ready made for calculating the eigenvalues in the eigen functions. For example, the match slice from Ledoux and Van Dyle, for which we'll discuss some details now. Match slice is a MATLAB package, and also there is a Python package for this called PySlice. It's similar to compute the eigenpairs of regular and singular self-adjoint Sturm-Liouville eigenvalue problems. And let's see a quick example. We consider this differential equation for a potential having this exponential or form, together with the Dirichlet conditions on the boundary. And by using a match slice GUI, I'm not sure if it's clear here. This is a GUI graphical user interface from MATLAB, where one can input the potential and the boundary conditions, and then print the eigenvalues and also plot the eigenfunctions. So there are many easy ways to calculate the eigenvalues and the eigenpairs for regular and singular Sturm-Liouville problems. On the other hand, for the transmission eigenvalue problem, since its high complexity and difficulties appearing, only the last 13 years we have seen results and works about that. The first paper was due to Colton, Mock and Son in 2010, where they developed some finite element methods to accurately approximate the eigenvalues from some cases or domains. I think it was disks and squares. And since then, more sophisticated methods like spectral methods or even discontinuous Galerkin methods. Also, boundary integral methods have been developed for the calculation of the eigenvalues for non-refractive index. So this is a very growing field in numerical analysis, and it's still ongoing, and it's a lot of results are still coming about solving the direct eigenvalue transmission eigenvalue problem. Here we're going to briefly show some results from an old paper we had with Professor Joseph Gididis. Also, it was a part of my PhD thesis, which is based in a Galerkin method to approximate the eigenvalues in general domains. And the main idea is the following. We can rewrite the boundary eigenvalue problem in the following fourth order equation for an operator of the fourth order, as we see in the first line, which now, this problem has a simpler homogeneous boundary condition for this function u, which will be the difference between the fields W and V appearing in the coupled system we saw initially. And this u must be in the Hilbert space H02, and the refractive index could be even in L infinity. For this fourth order equation, we can rewrite it in the following variational form for test function in the same Hilbert space. And an idea to solve the problem is to create a Hilbert basis in the space. A good choice for this is the eigenfunctions of the clamped plate, which is the Laplacian operator with homogeneous boundary conditions. And in the case when we are in disks, as the examples we're going to see in the following, the eigenfunction can be computed analytically. So, assuming we have this Hilbert basis, we do the Galerkin procedure as follows. We take a finite sub basis, and by using the variational form of the problem, we have the equivalent quadratic eigenvalue problem, where here this k of n is the approximated eigenvalue, and the matrices A, B, and C are square matrices n type n, and have the following good properties. All of them are symmetric. So we started from a non-self-adjoint eigenvalue problem to end up into a symmetric quadratic eigenvalue problem, where the first and the third are positive definite. And in that paper, we also show that the eigenvalues of the discrete problem converge to the corresponding original ones. And this was based on using some results from Babushka and Oz. So a quick example on this, we assume we have our domain is a disk in R2. So we have, and also we have a constant index. And we solve the direct problem as follows. We use the Galerkin method as described. We make a basis of 28 functions. Using those and integral numerical integration, we compute the matrices A, B, and C for a given refractive index, and calculate the approximated first eigenvalues here with MATLAB function polyi. And additionally, in the case that we are in a disk, we can also analytically compute the lowest transmission eigenvalues from separation of variables. So we have a target, let's say, value, which is the original ground truth eigenvalue, and then we compute the error. And some examples are here in the following table, where we see the original eigenvalue corresponding to some refractive indices of the unit disk, and the approximation error is very low, showing that our method works well in this simple case. Okay, and also we tested that in complex to get the complex transmission eigenvalues for constant and piecewise constant refractive indices. All of these are results found in this paper and in my thesis. So to this point, we have our model to solve the direct problems, both for transmission and Sturm-Liouville. And let's see how we're going to use this data to study the inverse eigenvalue problem with machine learning. The following are based on a very recently published paper by me and Andreas Dargaras. It was published in Computer and Mathematics with Application in January. And the main idea is the following, which is the key in all this procedure. As a first step, we used computational methods like those described before to solve the direct problems for a given set of physical parameters, which for are refractive indexes or potentials. and produce a dataset of approximated eigenvalues. Then we use these approximated eigenvalues together with their corresponding parameters, which are the refractive indices, etc., to train the machine learning algorithms. And this is called supervised learning because we give both the eigenvalues, let's say, and the target parameters to train the algorithms. Then we evaluate the performance of each algorithm. And in the end, if we also have a test of eigenvalue set coming from scattering data or analytically computed eigenvalues or different eigenvalues than those from those that we use for training the algorithms, we can also solve the inverse problem and check the performance on this set. And in general, it's good practice to study inverse problems for which uniqueness is secured, because this makes sense to try to train an algorithm using data for which you know there is some type of uniqueness. Now a quick comment about machine learning in general for inverse problems. Machine learning and inverse problems have been incorporated lately a lot in many different directions. For example, in problems of imaging and tomography, for example, I refer to this paper in inverse problems from Lee et al. In differential equations, especially what is so-called PINs, which is the physics in neural networks, which probably is the state of the art in machine learning, in scientific machine learning for differential equations, both in direct and inverse problems, by Raisi, Pallikarakis, and Kadianakis initially in 2019, for inverse source problems and many other directions. But for inverse spectral problems especially, there are only a few works previous to ours. For example, for the Schrödinger equation in a paper published in the International Journal of Quantum Chemistry by Lange and others. For the anisotropic Dirichlet operator by Sandon and others, and some more works in this field. So let me now describe the main idea of the supervised machine learning regression. The first thing to do is given a set of X data, which for us we're going to be the eigenvalues, and Y data, which are the target values, i.e. the physical parameters. We firstly divide our full set of X and Y into a training and validating subsets. So we divide the data. Then we use only the training subset to train the machine learning algorithms. This is usually it's an iterative procedure. And once the model is trained, we use only the X validation set, which are the validation subset of the eigenvalues. We give it as an input to the machine learning model, and we get an output, which are the predicted parameters, which, for example, the predicted refractive index or the predicted potentials, which we denoted with Y pred. Then we compare this prediction with the ground truth validating Y val, which is known because it was given in the original initial set. And these two sets should be, the prediction and the validation should be close enough. And I'm going to say something in the following about these closeness. And in the end, in the case when we also given a testing subset of eigenvalues, which are out of sample and might be of different nature of the training original set, we repeat the procedure to predict the Y test and thus solve an inverse problem. So how do we measure if our predictions are close enough to the original target values? And this is the prediction means with the solution of the inverse problem. And since we're studying regression models, we're going to say a few words about regression metrics. So assuming that we have n number of samples and Y pred I is the predicted target value and Y val I is the actual target value. Of course, the most typical way to see a reference about this is the mean square error, which is the average value of the sum of the squares between these two families. But especially in machine learning, the most usual metric to do it is called coefficient of determination, is this parameter R squared here, which is 1 minus the sum of square of the residuals versus the total sum of the prediction minus its mean value. So this parameter can be negative, and usually it's positive, and the closer to 1, the better the prediction. So we need coefficient determinations that should be close to 1. And okay, now I'm gonna take some time to briefly discuss the 3 models we implemented in this paper. Some of them might be well known. Just give the main idea without trying not to get into many details. And I refer to the classic book of Good Failure, for example, of deep learning for further details. So the first model we tested is called K-nearest neighbor. It's an old algorithm, maybe in 60s, I think. And the main idea is to, by using a predetermined number of nearest neighbors k, which is an input in the model, we make a prediction using these k closest distances for prediction. And the algorithm is quickly the following. We first load the data, which are our features x and target values y, which for us, I said before, will be the eigenvalues together with the target potentials or refractive indices. We choose a k, which is usually a small number. It's maybe 3 or 4, but this is also a hyperparameter, and the problem must be optimized, and either by trial and error or other methods, one could pick the best k. Then for each point xi we give, which would be, let's say, a vector of eigenvalues, we measure the distance between this input and all the data set, all other points. And then by selecting the k shortest distances, where k, as I said before, could be 3 or 4, for example. Then the prediction which we're gonna make is by taking the average of the target values of y of these k closest neighbors, and we assign this calculated average as a predicted target value for y. And in the end, to verify whether our prediction was good or not, we compare these predicted values y pred to the actual values of y, and by calculating either the mean square error or the coefficient of determination, as I explained before. The second model we used in our paper is random forest. Also, this is a very well-known machine learning method. It's an ensemble method. That means that we use multiple different models which are trained in the same data and take their average as an output. And these different models in random forest are called decision trees. Maybe it's something known to the audience, which are not like models, which are based on if-else condition to split the data, and this makes, in the end, a tree. And the algorithm quickly, without getting into details, follows. As previously, we input the dataset with features x and target values y. We randomly split the data doing by a method which is called bootstrapping. So we have our initial dataset, and by shuffling and splitting, we make n groups and new datasets produced by the original one. And for each of these datasets, we make one decision tree. So if we have n groups, we also have n decision trees, one for each. And the main idea, which is the core of this algorithm, is the decision tree, which the idea follows. The first thing to do when making a decision tree is to divide the starting data into two smaller data sets. And the division is done by using the features we have, which for us will be the eigenvalues, let's say, and doing if-else questions on the features, we choose the best split, which is the one that minimizes the mean square error between the target values within each subset. So we start with a big data set and we go to iteratively to smaller data sets. And the way to do it is trying to minimize, to get the largest reduction in mean square error. And this is done iteratively until a stopping criterion, which can be the depth of the tree or other criterions, which are parameters in the model. Then, for each new data point, the prediction is the average prediction from all trees. So whenever a new input, a new entry comes, we have one prediction for each tree, and the final output is going to be the average of all these trees. And as before, we access performance by using mean square error or coefficient of determination. And this is a quick example of a decision tree. This is a decision tree with depth 2. Of course, it's a simple educative example here. It's not the one we used actually, but this is produced by using the original data we had in the transmission and value problem. We see examples we're gonna see in the end. So we start, let's say, from the first node, which is the full data set from this 5, where it says that the sums are 59,000. It says so. We start from the full data set, and we want to divide it in two. And the way to divide it in two is to check all the features. So it's gonna be all the eigenvalues we have, and do a splitting in a way that the mean square error, the variance of the y values, the target values, is minimized. So we start from mean square error 3.6, and then we go to lower mean square error. And the best questions, let's say, to do the first splitting is whether the K1, the first eigenvalue, is less than 1.8. So this is the best question to do the first split, and this divides our tree in two. And this goes iteratively then into each subset until a stopping rule. And last, we used the multi-layer perceptron as a machine learning model. This is a specific category of neural networks, which are called feed-forward, where the information goes only forward and the connection doesn't form loops. And in this figure, we see an example where we have an input layer, which are our x values, the eigenvalues, two hidden layers, and the output layer, which are the y values, the target values. So the information goes from the input and propagates through the output. And these circles in each layer are the nodes of each layer, and each node has an activation function, which is a nonlinear function, and weights assigned for every input. And the aim of the neural network is to train these weights from the input data, so the prediction is optimized. And this is done with usually with gradient optimizers. And the weights are chosen so that the mean square error, the loss function, is minimized. And here is a quick idea of the algorithm. So again, we load the data, our x and y values. We in the first iteration, we randomly initialize the weights for each connection between nodes. And the first part of the learning model is called forward propagations, and is the following. We calculated these weighted sums here for all inputs xi for each neuron j in the hidden layer by this weighted sum, where wij are the weights. And then the output of each neuron is obtained by applying an activation function f. So in the previous graph, let's say I'm not sure if my pointer is shown. Anyway, let's pick the top node in the hidden layer 1. As we see, there are connections between this node here and all the previous nodes in the input layer. So if this node is j and xi are the input layers, the input nodes, for each xi is assigned a weight, and we calculated the weighted sum. This weighted sum then is outputted to the hidden layer neuron through an activation function. So we started from eigenvalues, we assign the weighted sum of inputs, and then this is outputted with a function f, which is a nonlinear activation function. And this is repeated in all nodes, in all layers until the output layer. Then we're still in the first iteration. We calculate the loss, which is the mean square error between the first output we have and the ground truth actual y values. Then we go to a procedure called bar propagation, which is the target for this procedure is to update the weights in order to minimize the loss. And this is done using computing the gradients of the loss function with respect of each weight, these wij weights. And this optimization procedure is done with gradient descent type iterations. So gradient descent type algorithms, sorry. And then this was only the first iteration, this is repeated iteratively until convergence. And with convergence here, we usually mean either a number of steps, or we stop learning once the loss function is not further reduced. And once the model is trained, the weights are fixed. Every new entry, every new x, every new eigenvalue vector we give to the model, we get an output, and this is the prediction, which is the solution of the inverse problem, actually. And as we did in the previous model, we assess performance using mean square error or a coefficient of determination on this validation set. And now let's see the examples we studied. We will see three different cases. Firstly, for the Sturm-Liouville eigenvalue problem, we chose this example of symmetric potentials with Neumann conditions. So for each B, we have a different potential here. And the idea was the following. Firstly, we use match slice, as explained initially, to solve the direct problem and compute. We needed only the first 5 eigenvalues for a family of potentials of B between -20 and 20 with step 0, 0.4. Then we also discretized our potentials Q in 21 points of the domain of definition. So doing these two discretizations, we get a data set of 1001 samples, which the eigenvalue matrix X consists of 1000 samples and 5 features, 5 eigenvalues, while the target matrix Y consists of 1000 samples and 21 target values. So these are our X and Y's in the model. Then we randomly pick the 70% of this data set for training, and then the 30% for validating. This is a common practice. It's a common division in the data set. We always take a larger sample for training and a smaller for validating, which could take, let's say, 80-20 or 75-25. And this is usually done by trial and error. This is the most advisable, let's say, splitting for this type of problems. Then we use this 70% for training, which means that we use both X and Y of this 70%. So we train the model, and then we check with the validation set, which are the validation X eigenvalues, let's say, of this 30%. And additionally to that, we also created 4 examples for 4 different values of B, which these B values are not included in the training set. So these are completely unknown to the algorithm, let's say. And we tested these 4 potentials and solved the inverse problem for these 4 potentials to see the results. And we have the following. Let's have a look firstly on the table on the top. So these are the R-square regression scores, the coefficient of determination, both for training, validating, and testing, for all the 3 models, KNN, RF, and MLP we used. One thing which is really important in these applications in general machine learning is that the results in training and validating sets should be close enough. And this means that the algorithm is not overfitting and it's learning well, and it's possible to generalize to the unknown data set. And also in the test, these are the results coming from these 4 different potentials we see in the bottom, which these are the 4 different potentials we tested also in the end for these 4 different values of B. And with the red, we see the ground truth original potential values. And with the other 3 curves, we see the predictions, which are almost identical, and the results were pretty good. For the transmission eigenvalue problem, which are the following examples, we tested the case where D is a spherical symmetric domain in our disk with L number of layers, and the refractive index is a piecewise constant function with different values in each layer. So we'll see 2 different examples in this case. And when the domain is spherically symmetric, as I also mentioned initially, we can analytically compute the transmission eigenvalues using boundary conditions, which is by using separation of variables. So for this case, for the transmission eigenvalue problem, we have the Kalerkin, let's say, method to approximate to to calculate approximated eigenvalues, and also an analytical method to compute original ground truth or eigenvalues coming from maybe scattering data, which could be close to these values. We will see two examples. The first one is for a two-layered unit disk. So we have a unit disk with an inner disk and one layer, and the refractive index is piecewise constant. The idea is the following. We solve the direct problem by using the Pallikarakis method I described before, and we compute the six first real eigenvalues for a refractive index with values Ni1, Ni2, the values of the refractive index, and D, which is the position of the discontinuity, which is also an unknown, and we want to recover it in the index problem. We took a family of refractive indices between 2 and 10, and discontinuities between 0.1 and 0.9 in the unit disk. So we allow the discontinuity to be through the disk. And by taking all the possible combinations, this produces a data set of 59,000, let's say, samples, which our X matrix again are the six eigenvalues of these 59,000 samples, and our Y matrix, the target values, are the values of the refractive index and the position of discontinuity. And again, we do the same idea with splitting. We shuffle the data and randomly divide into training and validating, which are 70% for training and 30% validating. We train the algorithm with the algorithms with this 70%, and then we check with the 30% X values, the 30% validating eigenvalues. And in the end, as we did in the Sturm-Liouville problem, we checked also with eigenvalues which are not initially included in the dataset, which for us are coming from separation variables. So besides testing the validating set, we also tested the model with in 10 different refractive indices, using 6 original eigenvalues in each case from separation of variables. And the results follow. Let's focus again on the first matrix, which are the coefficient of determination scores. We see again the training, validating, and testing columns for all three models, KNN, random forest, and neural networks. We again notice that the training, validating results for R-squared are close, which is good, and also that in the testing subset, the results are good and are shown in the graphs below. So in the first graph on the top, on the left, top left, is the refractive index Ni1, the refractive index in the disk. In the second is the refractive index in the layer, the outside layer, and the third is the discontinuity, where we see that the refractive indices are very well covered, and the discontinuity is less stable, which is reasonable because it's harder to recover its position. But and at this point, I would like to mention that it's really important that we have a model trained with approximated data, and then we also in which it performs well. So if there is a proof of concept that indeed machine learning can be trained, models can be trained by eigenvalues in association with the refractive indices. But we also tested in eigenvalues which have different nature because they are original, are analytically computed, and the algorithms are still performing well. And the second and last example we included was a 4-layer unit disk. So our disk now has 4 layers, and the procedure is similar more or less. We use the Pallikarakis method to solve the direct problem, and we compute 6 eigenvalues again, the first 6, for possible combinations of the refractive indices Ni1, Ni2, Ni3, and Ni4 for each layer. We chose a family of refractive indices between 2 and 10 with step 0.25, and in this case the discontinuities are fixed. So we assume that the discontinuities might be at 0.25, 0.5, 0.75. All these possible combinations produce a very big data set, which more than 1 million samples, consisting of 6 features, 6 eigenvalues for X, and 4 target values for Y, which are the 4 values of the refractive index. Again, the procedure is the same. We split in training and validating, train the algorithms with the training and check with validating, And again, we solve this inverse problem with original eigenvalues in the end, coming from separation of values for 10 examples. And the results are here in the top table. Again, we see the output of the R squared for training, validating, and testing. One quick comment here is that the neural network outperforms the other models because both training and validating the MLPs are very high. And this is a classical result in deep neural networks because the larger the data set, the better the predictions, the better the model performs. And for that reason, deep learning is better in a large data set compared to other simpler models. And in the bottom, we see the predictions for the four values of the refractive index, which are new 1, E2, and E3, and E4, where we see that our predictions are good. And this also is done in original eigenvalues, not included in the approximated data sets. So at this point, a quick summary of what we discussed today. We discussed about direct and inverse Sturm-Liouville and transmission eigenvalue problems, and we saw some definitions, and we briefly discussed about some non-numerical methods to solve them. And the main part of my presentation was focused in the ideas of supervised machine learning regression. I try to explain quickly in a short seminar, let's say, the main idea behind KNN, random forest, and MLP. Then I saw how we use supervised machine learning models to adapt them in inverse eigenvalue problems. And in the end, we saw some example of application of these models to solve inverse Sturm-Liouville and inverse transmission eigenvalue problems in special cases, for which we also have some unique results. And here are the main references. The first two are for the direct transmission eigenvalue problems back to 2013 and 2017. And our latest work about the application of machine learning to inverse eigenvalue problems, as I also explained. I would like to thank you for your attention, and I'm looking forward for comments, questions, and ideas.